Hello, I'm Nicholas Dwork, and today we're going to be discussing parallel imaging. We previously saw that MRI primarily measures the amount of water at each location. We will now see that the antennas used to measure the signal also affect the image's appearance. The antennas we use are coils in MRI. They're little loops of wire, and they're underneath plastic to make the patient comfortable and prevent any burn. Here's an example of one coil. It's sold by Philips, and it's meant to make very high-resolution images like that shown here of the knee. So it's exquisite resolution, but it doesn't see very much stuff. Here's a Philips Elysian 3 Tesla scanner. The patient lies down on the blue bed and then is moved into the bore where the patient is imaged. Underneath of the plastic sheathing of the machine is a coil used for sensing. It's called the body coil. So it can see a lot of the patient, but it doesn't get very high resolution. Generally, a coil sees things that are close better. So here's an example of a knee. This is similar to the example I showed you before, and maybe you noticed this issue then. We'll discuss it in full now. Here are two different locations of muscle. They're very similar muscle. Presumably they have about the same amount of water in them, and yet they're different brightness. The arrow pointing towards the top is pointing to a location that's much darker than the arrow that's pointing to the bottom. Why is that? Just from the brightness across the image, we can see that the coil was placed near the back of the knee. And so it senses things close to it better than things that are farther away, so it gives this shading across the image where things to the lower right are brighter, and then as you move distant from that, it gets darker. So what if we wanted to see a large amount of the body, but we also wanted to see it with high resolution? What can we do? The answer is coil arrays. Here's an example of a 4-channel coil array. So there are 4 coils underneath this rubber cover. This is a flexible coil array currently sold by Siemens. Here's a new state-of-the-art for MRI. These are screen-printed flexible coils. They're imprinted onto plastic. And then these are placed under blankets to make it especially comfortable for children. Because the coils are so close to the children, they also make better images. Here's an example of an ankle coil. It's an 8-channel ankle coil used on GE systems. Here are 8 images of an ankle taken by this coil array. So we can see roughly where different coils were located. Coil 7 was located near the toes, while coil 1 was located near the heel. With these 8 images, we can just add them up together, and then we get a high-resolution image of a larger field of view. Here's a 8-channel birdcage coil, also for a GE system. Here are 8 images of a knee captured with such a coil array. Again, you sort of get a rough understanding of where each coil was relative to the knee. And what we can do, like we did before, was just take all these images, add them up together, and we get a high-quality image of a much larger portion of the knee. However, this takes quite a long time. If you're doing this in 3 dimensions, it takes an extremely long time, and we want a way to speed things up. The multiple coil array gives us such an opportunity. And here I'm going to show you an image that was reconstructed from data taken about half the time. And you can see that the image is about as diagnostic. It's about as good. So how does this work? Going back to K-Space, here I'm representing a 2D grid of data collected with the MRI machine. Each of these gray circles represents data. In order to reduce the amount of time of the scan in half, we'll only collect every other column of data. That is, we'll avoid collecting even columns of data. Since we're not collecting the data, we don't have to spend the time. Now, if we just reconstructed this image, as shown in a prior lecture, this would lead to aliasing. So how do we avoid that? It turns out that the missing values are an average of the nearby values. So all we have to do is compute this average, and we get an estimate of the missing point. So we do that for the first missing value, slide down 1. Take the same average for the next missing value, slide down 1, take the same average, and we'll do that for all missing points until we've filled in K-space, then performing an inverse discrete Fourier transform recovers our image. So, with multiple coils, you can increase your field of view while maintaining resolution. You can also take advantage of parallel imaging to reduce the scan time required. Thank you for your attention.